Alright, hello everyone. Starting from the Spivak calculus. Last time we finished on the distributive law and its implications on numbers, and the fact that a lot of operations rely on distributive property of numbers. And we'll continue from that section of the Spivak calculus textbook. Let's get down to it. So from last time we'll learn that got a textbook calculus on me one with me. Let's get reading on it. From here, it's page 9, basic properties of numbers. The properties P1 to P9 have descriptive names which are not essential to remember, but which are often convenient for reference. We'll take this opportunity to list properties P1 to P9 together and indicate the names by which they are commonly designated. We have associative law for addition, existence of an additive identity, existence of additive inverses, commutative law for addition, associative law for multiplication, existence of a multiplicative identity, existence of multiplicative inverses, commutative law for multiplication, and then distributive law. The three basic properties of numbers which remain to be listed are concerned with inequalities. Ooh, exciting stuff. Although inequalities occur rarely in elementary mathematics, they play a prominent role in calculus. The two notions of inequality, A is less than B and A is greater than B, are intimately related. A is less than B means the same as B is greater than A. Thus 1 is less than 3 and 3 greater than 1 are merely two ways of writing the same assertion. The numbers A satisfying A is greater than 0 are called positive, while those numbers A satisfying where A is less than 0 are called negative. While positivity can thus be defined in terms of less than symbol, it is possible to reverse the procedure. A is less than B can be defined to mean that B minus A is positive. In fact, it is convenient to consider the collection of all positive numbers denoted by P as the basic concept and state all properties in terms of P. Okay, so for every number A, only one and only one of the following holds. A is equal to 0, or A is in the collection of positive number P, or negative A is in the collection of positive number set P. So one of the three holds is one property, and P11 says if A and B are in P, then A plus B is in P. Closure under addition, because when two numbers are in positive number set, their sum are also in P. Closure under multiplication, when two numbers are multiplied and both are in P, and then the product of them are also in P. Okay, seems like pretty intuitive stuff. These three properties should be complemented with the following definitions. A is greater than B if A minus B is in P, and A less than B if B is greater than A is greater than or equal to B if A greater than B or A equal to B. Same thing, the opposite way. Note in particular that A is greater than 0 if and only if A is in P. Right. All the familiar facts about inequalities, however elementary they may seem, are consequences of P10 to P11, P12. For example, if A and B are any two numbers, then precisely one of the following holds. A minus B is equal to B, A minus B is in the collection P, negative of A minus B is equal to B minus A is in the collection P. Using the definitions just made, it follows that precisely one of the following holds. A is equal to B, A is less than or greater than B, or B is greater than A. A slightly more interesting fact results from the following manipulations. If A is less than B, so that B minus A is in P, then surely B plus C minus A plus C is in P. Thus, if A is less than B and A plus C is less than B plus C, similarly, suppose A is less than B and B is less than C, then B minus A is in P, C minus B is in P, so C minus A is in P. Alright, this shows that if A is less than B and B is less than C, then A is less than C. The two inequalities A less than B and B less than C are usually written in the abbreviated form A less than B less than C, which is the third inequality, A less than C, almost built in, right? The following assertion is somewhat less obvious. If A is less than 0 and B is less than 0, then A times B is greater than 0. The only difficulty presented by the proof is the unraveling of definitions. The symbol A less than 0 means, by definition, 0 is greater than A, which means 0 minus A is equal to negative A is in P. Right. Similarly, negative B is in P, and consequently, by I was just thinking what it all means. The thing is that when something is in P, it's basically the same thing as say if A is in P, element of P, that means A is in fact greater than 0. That's the definition of it, right? So we don't have to think it in the separate terms. Something is in P in the positive number set, that means that A is greater than 0. Okay. So he briefly touched upon something that's not very obvious, less obvious. The only difficulty presented by the proof is the unraveling. So here, A is less than 0. It means that negative A is in P. Similarly, negative B is in P, and consequently by P12, negative A times negative B is in P. Thus, AB is in P, is greater than 0, right? Because it's negative times negative B is positive, same thing as positive, so as we have proved it previously, so AB is greater than 0. The fact that AB is greater than 0, if A is greater than 0, B greater than 0, and also if A less than 0, B less than 0 has one special consequence. A squared is greater than 0 if A is not equal to 0. Thus, squares of non-zero numbers are always positive, and in particular we have proved a result which might have seemed sufficiently elementary to be included in our list of properties, which is 1 is greater than 0, since 1 is equal to 1 squared. There is one slightly perplexing feature of the symbols greater than or equal to and less than or equal to. The statements both are true, even though we know that less than or equal to could be replaced by less than in the first and by equal in the second. This sort of thing is bound to occur when less than or equal to is used with specific numbers, the usefulness of the symbol is revealed by a statement like Theorem 1. Here equality holds for some values of a and b, while inequality holds for other values, right? Was it obvious to us that a squared is greater than 0? Yeah. The fact that negative a is greater than 0 if a is less than 0 is the basis of a concept which will play an extremely important role in this book. For any number a, we define the absolute value of a as follows, which is equal to a if a is greater than or equal to 0, or negative a if a is less than or equal to 0. This definition is important throughout the textbook. Note that a absolute value is always positive except when a is equal to 0. For example, we have absolute value of negative 3, which is 3, absolute value of 7, which is 7, and 1 plus square root of 2 minus square root of 3, which is equal to 1 plus square root of 2 minus square root of 3. And 1 plus square root of 2 minus square root of 10 is equal to square root of 10 minus square root of 2 minus 1. In general, the most straightforward approach to any problem involving absolute values requires treating several cases separately, since absolute values are defined by cases to begin with. This approach may be used to prove the following very important fact about absolute values. For all numbers a and b, we have absolute value of a plus b is less than or equal to absolute value of a plus absolute value of b. Before we just to start looking at the proof by ourselves, let's solve it ourselves, because that's the most effective way for us to learn, right? So let's do that. Theorem is absolute value of a b is less than or equal to absolute value a plus absolute value of b. Why is that? Let's start with some of the cases. First of all, absolute value of ab is equal to a plus b if a plus b is equal to or greater than 0, or minus a minus b if a plus b is less than 0, right? And definitions for each of those terms are also the same. A minus a if a is greater than or equal to 0, minus a and negative a if a is less than 0, and b itself to have the same result by their definitions. So let's consider the case where both are positive, right? If both a and b are positive, let's write down the case by case. Case 1, a is positive or greater than 0, and b also positive or greater than 0, or equal to 0. Some misnomer here, because I have to include the 0 too. Well, in fact, when there is 0, we don't have to maybe we need to take care of some edge cases in a plus b, but we'll get to that later. So when they're both positive numbers or 0, a plus absolute value of a plus absolute value of b is equal to a plus b. How about a plus b itself? This is in positive because since A is positive, B is positive, so A plus B is also positive, which means that absolute value of A plus B is equal to A plus B, right? So this means that they are equal because they represent the same thing when A and B are both positive. Consider the case where A is less than 0 and B is less than 0, right? Then A plus B A plus B, absolute value of A plus B is minus A plus minus B, right? Then, well, this comes from the fact that it's negative times a negative of A plus B, and by discrete property, it's minus A plus minus B, right? And this minus A is the same as absolute value of A because right now A is less than 0. And the second term here means that negative B is same as the absolute value of B, which indicate that these absolute values are in fact equal. So let's consider a little not very intuitive, maybe intuitive for some, but not intuitive for me at least. The cases where 1 is positive and 1 is less than 0, right? I was just thinking this a little different thing. Well, something is 0, then we don't even need to take care of it because let's take care of it. When A is equal to 0 and B is less than 0, then A plus B, absolute value of A and B is absolute value of B, which is negative B. This is also the same thing as absolute value of B, right? But absolute values are always positive, so when we add some positive number, which is 0 in this case, however, which is absolute value of A, this one is 0, so it's a additive additive identity, right? That doesn't change the anything on both sides. So this again satisfies the inequality statement. It's equal. So now one of them is positive and one of them is negative. Given that fact that we've cleared up the edge case where one of them is 0. If both are 0, or both sides are equal to 0, so we don't have to write it down whole thing. No, we will understand it. If both are 0, then the statement is yes, true. When A is positive and B is negative, how do we deal with these? Let's see. A plus B is equal to, we don't know what it's equal to. So I put it a question mark, but we know A absolute value of A is equal to A, and absolute value of B is equal to negative B, right? So A plus absolute value of B is equal to A minus B here of course it depends really on what they mean. Well, it is true that a minus b is equal to greater than 0, right? Because we're taking absolute value of b, where b is less than 0. So minusing on b makes this whole thing positive. What else? But I guess what matters is now which one is greater. So without loss of generality, could be either one. So let's see. Let's just say absolute value of a is less than absolute value of b. In that case, um, absolute value of b minus absolute value of a is equal to is greater than 0. Um, hmm. Let's expand this a little bit. Right. Okay, let's think about this for a second. What is absolute value of a plus b? It's a plus b, or minus a minus b. If a b are equal to greater than 0, if a plus b is less than it's 0. So we just assume that absolute value of a is less than absolute value of b, which means that a is greater than 0. So a is less than uh, minus b, because absolute value of b should be minus b. Okay, so granted that, that means that a plus b is in fact less than 0, right? So it has to be that for this current state of absolute value, where we are assuming that absolute value of a is less than absolute value of b, this value has to be minus a minus b. What does that leave us? This leave us because this leave us to, does it leave us to the statement where it is less than or equal to absolute value of a plus absolute value of b? Is it true? Well, let's see. A is less than A's A, and B is negative B. So we can remove this, and 2 A is 2A is greater than 0. So A should be greater than 0. Okay, got it. So we can start from the fact that um, uh, A is greater than 0 to prove the last case. A is greater than 0. That means 0 is less than 2 times A. Because 2 is positive and A is positive, both are positive by the closure. And B can plus B both. Wait a second. Yeah, we can do plus minus B on both sides because they're the same. No, it's not the same thing. What am I talking about? Yeah, same thing. This means that when you're adding both sides, same thing on both sides, the inequality still holds. Well, to be precise, we didn't have this adding things on both sides yet, so let's do this. 0 is less than or equal to 2a plus 0. And 2a plus 0 is basically the same thing as 2a plus b plus minus b, right? Negative b. And then that is the same thing as the saying b is less than or equal to 2a plus b, right? Alright, so now we can do b minus a plus b, because we're removing 1a from it, and no way, what am I talking about? I'm a little confused, but it's okay. It's not very organized. A is less than B, but B is negative. But B is negative. Okay, let's do this again. Let's do this again. Remove all. Sorry for not being structured enough. You can start from the scratch. So the case where A is positive and B is less than negative, B is less than 0, we don't have to go to save the case where B is B is greater than 0 and A is less than 0, greater than 0, less than 0, because we already, if you prove this case, then we don't have to do that because we can just flip around A and B, right? So we'll try to take care much attention to solving this one. So from this we know absolute value of A is equal to A because A is greater than 0, and absolute value of B is negative B because B is less than 0. And the thing about absolute value of A plus B, we know nothing about yet because it could be either positive or negative, right? So it really depends on the case where is absolute value of A greater than or equal to B, right? It could be either A is less than B or B, absolute value of B is less than A. Yeah, both are positive, but it really depends on where in the number line they stand. So we can conclude what A plus B it is. Okay, so we know, let's assume 1. We'll go to 2 later after we finish the number 1. So that means A is less than minus B. That means that A plus B is less than 0. So that means absolute value of AB is equal to A minus B. Where does that leave us? We need to compare this value to A plus negative B, right? So first of all, minus A minus B is less than, it is a positive value, right? It's a positive value. Let's think of it in that term because it's an absolute value. And then That means that minus a minus b plus um, a well, the idea is, can we prove that a minus b is equal to or less than a plus negative b? Can we do that? Yes, we definitely can. It's p. And then by closure, we can say that a plus minus b is greater than 0, right? By closure, right? So that means that a plus minus b is greater than a plus b. But that's not what we're trying to prove here. A minus a plus minus b. Actually, this is not it. The thing I'm trying to prove is a plus negative b is greater than 0, which means b minus a this is not what I'm trying to do. Oh my gosh. Okay, let's do this again. Let's do this again. I'm just making myself more complicated than it is. So a is greater than 0. So a, absolute value of a is less than absolute value of b, which is negative b. This means that minus b is less than or equal to negative b minus a is greater than 0. Would you leave us? Okay, I'm gonna pause for a few minutes and come back when you solve them. 1 second. Please give me like 5 minutes. I'm gonna pause. Okay, everyone. Although I think I come up with I can't come up with a better solution. This is the best I can do at this time and moment. One case is if absolute value of A is less than absolute value of B, that means that absolute value of B minus absolute value of A is greater than 0, and that means that by definition of the absolute value of B and absolute value of A, 0 is less than or less than minus B minus A, because this is the case where we are assuming A is greater than 0 and B is less than 0. So that means by the in another means, this is the B plus A, negative of B plus A is in P, which in other words, B plus A is less than 0, right? So that means the absolute value of A plus B is equal to negative A minus B by the definition of the absolute value here. And then because A plus B is negative A, negative B, negative A minus B, this is less than or equal to A minus B, because we're instead of subtracting positive value, where this is how to explain it. So so negative A minus B is basically less than minus b, because minus a is we're subtracting the total value from minus a minus b. So it's less than negative b. And if we plus a from here, then obviously this whole value is less than minus b plus a, right? Because this total value is the plus a from the same value we just calculated. So this inequality so satisfies with this is basically equal to absolute value of a plus absolute value of b. So inequality is a little bit more is more thought out process. The best case is you consider all the cases. I think I didn't do a very good job at explaining the last cases. If you do the last cases though, it's good. We don't have to prove where 1 is greater than 0 and 1 is less than 0, because this covers all. But if I come up with a better solution after reading the Spivak textbook, then yeah, I will definitely re-upload it. But thank you for watching. This is Spivak Calculus Basic Properties of Numbers. We'll move on to the next one in the next video. Thank you.